All right, we are here looking at sequences. This is pretty much review for you guys, so hopefully it's gone easily, but just wanted to review a few things. We're just asked to find out, are these sequences convergent, meaning as n gets bigger and bigger and bigger, will it approach a value? Can we, by making n sufficiently large, get as close as we'd like to a particular fixed value, or maybe it'll go up to infinity. So what's happening here? Well, as we look at this, we've got 3 to the n plus 2 over 5 to the n. Okay. Well, I think the easiest way to look at this is really we're basically raising two things to this n. This little number here, 2, is not going to amount to a hill of beans in this world when we get bigger and bigger and bigger. So essentially, it is 3 to the n over 5 to the n, which is the same thing as 3 over 5 to the n. And so in this case, we clearly have a fraction that is being multiplied by a larger and larger and larger and larger number as n gets sufficiently large. So we are really looking at this n plus 2 and reducing it to n using some kind of common sense reasoning when it comes to math that I've got down here in terms of growth rates. All right, so I think it is really useful to sort of have a hierarchy of these values, and it can help us place things along the lines of, who's going to win in a battle between n raised to the p power, for instance, as n gets large, or p raised to the n power. And if you look, this sort of should make sense. As we take the log of something with an exponent, that's really a way of reducing it by an exponential value in a way. So this is greatly reduced, ln of a number. So we can get to 10,000, and when we take the log of it, we've really reduced it just to the exponent that gets you up to 10,000. All right, so here is a fixed number, a number that's getting larger, going to a fixed exponent, and here's a fixed number going to a large and large and larger exponent. This is n to the factorial, so as n gets large, n factorial gets very large, and this is the champion of them all, n raised to the n power. Okay, and you can do crazy things like raise something n to the nth power, but these are things that we'll run into in practical terms. So conversely, or I should say inversely, if we put 1 over these things, then 1 over n to the n is smaller than 1 over n factorial, which is smaller than p raised to the nth power over, which is smaller than 1 over n to the p, and still smaller than 1 over ln to the p power. All right, so just as an example, what does this all mean? If we just simply look at a case where p is 3 and n is equal to 10, then the ln of 10 to the third power, okay, is going to be smaller than 10 to the third power, which is 1,000. By the way, the ln of 10 raised to the third power is 12.2 approximately. 3 to the 10th power then gets much bigger. 10 factorial is much bigger still, and 10 to the 10th is a 1 with 10 zeros. So again, this gives you a sense as to what things get big and how fast they get big. Get used to this, get comfortable with this, and by doing our homework, hopefully you will. So coming back to this now, we've got e that's raised to a 1 over n. As n gets larger and larger and larger, this is going to infinity. Even though we're taking the square root, it's not stopping it from doing that, so it's still going 1 to infinity. Well, that's approximately, or it's getting closer to, I should say, e to the 0, which is getting closer to 1. So that is convergent. This converges, by the way, on 0 as you multiply. This converges on 1. Well, what is this doing? Is this converging? Well, I think it helps to do a little bit of algebra here. We have got this, and this is no different than 2 to the 1 plus 3n, then raised to the 1 over n power. Remember, our radicals are the same as a rational exponent. Well, if I remember my simple rule of exponents, I multiply these, so that's going to be equal to 2 to the 1 over n plus then 1 over n times 3n plus 3. Well, that's the same thing as 2 to the 1 over n, and then times 2 to the third, which is just equal to 8 times 2 to the 1 over n. Well, as n gets larger and larger and larger, just like this one here, that's going 2 to the 0. So this is just approaching 8. So these all three are convergent. All right. There are plenty of examples that aren't. They're simply numbers that are getting bigger. If this was 5 over 3, of course that would be getting larger and larger and larger, not converging. So check out those examples. All right. 8.2 is on series. All right. Series is where we're summing up. We're adding up a certain number of these terms. The ones that are interesting for us are the infinite ones. So we're trying to find out, are infinite series going to converge? Will their sum converge on a fixed value? All right. So in order for things to converge, we know that the individual terms must converge to 0. So the individual a sub n's must go to 0 as n goes to infinity. Okay. It's not enough just to have it go to 0, however, because a famous example, in case, well, I guess I can come back to maybe my boundaries now to talk about this. In some of the ones we did just above, if you have a geometric series and if you know that that radius is less than 1, then that limit will be 0. A geometric series, remember, is in the form of some initial term and then your ratio between the terms to some exponent n, maybe it's n minus 1. That's going to be your geometric series. Well, if this radius is either less than a positive 1 or greater than a negative 1, it will converge, because essentially think of it as you're multiplying by a decimal and it's getting smaller. You're taking a fraction less than 1 each time. Another famous series is called a p-series, and that's where we have 1 over x, but x can be raised to some exponent. All right. This is always going to converge. These series will converge when we sum these up as long as p is greater than 1. 1 over x is the harmonic series, and this is an example of the individual terms going towards 0, but we're summing up these terms. It can be like 1 plus 1/2 plus 1/3 plus 1/4. This is the harmonic series. This does not converge. Even though these individual terms are going to 0, they're not going to 0 fast enough. So this series 1 over x is the famous one that converges. So know that, be aware of that. Okay. So what's happening here? Well, is this convergent, or is it, if it's not convergent, then it's divergent? So in this case, these numbers here become less and less important as n gets large. So essentially, this is really saying, is n over 3n going to converge? Well, no, that's going to get closer and closer to 1/3. So if the individual terms do not go to 0, then this diverges, because you're adding up terms that are essentially 1/3 plus 1/3 plus 1/3 an infinite number of times, and of course it'll eventually, not eventually, it is going towards infinity. So what's happening here? We're adding up the cosine of 1 over 1 plus then the cosine of 1 over 2. We're adding up individual things where 1 over n is going towards 0, and then the cosine of 0 is going to be 1. So essentially, in the end, we're adding 1 plus 1 plus 1. So this one also diverges. This guy, the cosine of 1 is just a number, and of course the cosine of any number is going to be less than 1 unless it's pi over 2, and it is not pi over 2. So we know that this is less than 1. Less than 1. So this is just a geometric series where because it is less than 1, it is going to converge. When they ask us to find in our text what is the sum going to be, well, the sum is going to be, according to that formula for the sum of an infinite series, it's going to be that first term all over 1 minus r, which in this case, the first term, if I plug in 0, the first term is 1, and then it's 1 minus, let's see, if I plug in 0, is that the, yep, yeah, the first term would be 1, and then cosine of 1 is my radius, because that's just what I'm multiplying by repeatedly. So whatever this value is what the sum is. Alright, then this last one is interesting. It's asking us to look and see if this can be written in a telescoping form. This is what's called a figurate pattern, it's a quadratic, and we can try to do these if we can break this down into partial sums. This one does break down. We can write this as 1 over n plus 1 minus then 1 over n minus 1. If you think about doing that, multiply these, I get that n squared minus 1 like I should, and then when I multiply these and I do the subtraction, I get n minus 1 minus n plus 1. Whoops, I should switch these around. That should be minus and that should be plus, because then I would get n plus 1 up there minus and n minus 1 right there, and I bring that minus sign in and I get a minus n and an n cancel, and then I get a minus 1 gives me 2 over n squared minus 1. Okay, well, having sorted that out, now I'm really asked to find out, well, what is the sum from n equals 2 to infinity? Note that that's 2. That's because we'd have division by 0 problems when we did this if we had it higher. So this is then going to be 1 over n minus 1 minus 1 over n plus 1, which then will be, if we start filling in for 2, it's going to be put in 2 there and I get 1, and then minus, and I plug in 2 there, 1/3, that's the first term, and then I add to it the second term. When I plug in 3 right there, I get 1/2, and then minus, then that's 1/4, and then I add to that 1/3 minus 1/5, and so on. I'll just do one more term. Well, maybe I won't. I think we got the idea. But notice that it's going by a regular interval of 2, so it's very predictable. I have a minus 1/3 here, but I have a plus 1/3 there. So if I break down these parentheses, I know that this is going to cancel with that. And actually, let me do one more. Then this would be 1/4 minus 1/6 dot dot dot. So then this minus 1/4 will cancel with that plus 1/4. And I know that then this minus 1/5 will cancel with the next plus 1/5. And what I don't have canceling is this term here and this term here. Everything else will cancel, and then at the end I'll have sort of the leftover part of my expression here, 1 over n minus 1 minus 1 over n plus 1. But of course, as n goes to infinity, these just go to 0. So I'm left with 1 plus 1/2, and that is indeed the limit. This is 3/2. So it converges. Telescoping, we can show that it converges to 1.5.